It's a little ironic, isn't it? We have this box, and I'm an outside-the-box thinker working inside the box, and here we have it. But irony has always been my strong suit, so there you go. And this is owned and operated by the Republic of Kiribati. And Christine is obviously a Kiribati native here in the audience. Is there anyone else here from Kiribati? Okay, well, we have one. Good job. Woohoo! Maori.
The natives are friendly.
All good. So the Republic of Kiribati is really a special country. They have a ton of ocean. And so they actually have 3 island archipelagos, which if you were to superimpose this on a continental scale, they would span the space of the United States or of Australia, just for scale. And they have 33 islands, which if you were to smush them together would have basically an area roughly the size of Baltimore, for lack of a better example. But this teal box in the center is the Phoenix Islands Protected Area, which, again for scale, is roughly the size of the entire state of California. Now, in the state of California, I actually meant to look up the population of the state, but I haven't. Does anyone know it offhand? I don't know. Well, there are only 26 people on average in the Phoenix Islands Protected Area. So can you imagine 26 people in the state of California? There's more than 26 people in this room. And so this is a pretty special place in the Central Archipelago. The vast majority of the country's population lives here in the Gilbert Islands on a Pacific island called Tarawa, and a decent, healthy population lives here in the Northern Line Islands group. So this is the protected area. And Greg is the world's expert on the conservation side, and I work on the science side of the house. And so I'm going to introduce you to this box from my point of view. Everyone always looks at the box, and the first thing that they're drawn to are the islands. And so the islands here are demarcated in black. There are 8 of them. And I want to show you a few other features. So first of all, these islands are small. They're either atolls or really tiny islands, and I'll show you them in more detail in a little bit. And they're spread out, right? You have 1 cluster over here and 2 over here. But you also have a lot of things that look like islands that don't have black names on them. And all of the ones named in blue are underwater seamounts that are also volcanic in origin and don't quite break the surface. And you can see you have an underwater mountain chain here. This is the Tokelau Ridge. And flanking this at the north and south are 2 special names written in white. This is Carondelet Reef and Winslow. And these are underwater seamounts that come all the way up to the surface and stop just about 5 or 6 meters below the surface. So they're mountains that are so close to breaking the surface but don't, which is a really unusual oceanographic feature or bathymetric feature that you don't see very often in the ocean. Here in the center, you also see this dark blue abyss, and this is a hadal hole or a hadal trough that exceeds 6,000 meters. The abyssal plain that you'll see throughout the rest is around 6,000 meters deep. And there are a whole bunch of other interesting features. For example, the equator runs here. So you have the equatorial current, the counter-equatorial current, and this just sits at a really interesting space on our planet. So let me introduce you in a little bit more detail to this. And can I get a little help in the back of starting this movie, please? Thank you. So this is the Phoenix Islands from the air, just 4 out of the 8. This is Canton Island. This is the only inhabited island. And you'll see some infrastructure on it. And it's because before Kiribati was gifted this land, it was owned by the United States and the UK, and it has all kinds of pretty interesting features on it. It has a big runway. It was part of the Pan Am hop across the Pacific. It actually has it's like a big satellite on it from the Apollo missions, the satellite tracking station, a bunch of old military infrastructure. And you can contrast that with this tiny island, right, where there's not a single tree. It's just an important bird nesting habitat. And this isn't sped up. This is just taken with a drone. This is real-time footage. And you can just sort of see what these islands have to endure. This is Carondelet Reef. This is one of those submerged seamounts that doesn't quite break the surface. And this is a really calm day. If you were here on any choppy day whatsoever, you wouldn't even be able to see it because the waves would mask its existence, right? And then you have places like this. This is Nika Maroro. This is one of the other large atolls, but fully uninhabited and thought to be the resting place of Amelia Earhart. So there are some pretty interesting spots. Can we stop the movie, please, and go to the next slide? I think I can do it from here. Perfect. All right. So you've had a little introduction. And of course, when I say the Phoenix Islands Protected Area, everybody always thinks about these islands. As you should. I mean, they're beautiful, they're stunning. They're atolls, they're volcanic in origin that used to break the surface, and then they've started sinking down. And so you have this lagoon where the island used to break the surface, and now you just see a ring of coral that's forming the sand around the edges. This was first described by Darwin. It was groundbreaking, and it's really, they are stunning to see. But they are so much more than just the islands, right? The Phoenix Islands protected area has 8 tiny little island specks, and the rest of it is ocean. And so when you think about the Phoenix Islands, you are thinking about it from a terrestrial point of view. But what I want to show you is the rest of it. And I don't know if I can. Here we go. Clicker. Of course I can. So there is a whole lot of stuff below the surface. You don't have to be lonely up there on the top, little man. There's so much below you. Okay. So there are so many things to talk about, and in the interest of time, I'm just going to break them into small vignettes and just show you, I think, what are the current crown jewels of where we are in our research program, and talk a little bit about the culture establishment, management, and conservation, talk a little bit about shallow coral reefs, a little bit about the pelagic open ocean, and a little bit about the deep sea. But please know that I could probably give 10 full-hour seminars on each of these topics, because after 10 years of research on my part and 5 years before that, and with everything we have planned for the future, this is an exciting place to work. So, Greg Stone, who's in the audience, worked for the New England Aquarium, and he was part of a Pristine Seas, or what was it called? Primal Ocean Project. You did work for Jerry Schubel at the time. See, it's all, you're among family tonight, really. And so he was part of a Primal Ocean Project to look for some places that were evocative of a primal space, right? Place before humans. And I'll let him tell the story if you want afterwards, but Greg decided to go to the Phoenix Islands protected area and explore it and take a look at what it looked like. And at the time, David O'Bura was a scientist who worked with him, and they did a great job of describing the habitat and sort of putting this place on the map and literally drawing the maps, naming sites, and laying the foundation. And when I got involved with this project in 2008, it was time for this burgeoning exploration to turn into a full-fledged science program. So we held the first science meeting in 2010, put a bunch of experts into a room and said, all right, guys, what are we going to do? This is a special place. How can we make it sing? And we came up with a bunch of priority areas, which include exploration, climate change, and connectivity. We knew we had to explore what we had. We hadn't fully done that. We knew that this was going to be an important place for climate change, given where it sits in the Pacific. This is a pretty interesting spot for El Nino and Southern Oscillation dynamics, which I'll explain in a little bit. And we knew that even alone in the middle of the Pacific, I mean, if we took any lessons from the Polynesian voyagers, of yore, it's that everything is connected across the Pacific. And we wanted to understand how that works in the Phoenix Islands as well. So we charted a 10-year course, and I'm delighted to let you know that we're still on course. We're about to finish up, and we're already planning our next 10 years of research. And so today I'm just going to tell you a little bit about some of these pieces. I also want to share that the Phoenix Islands Protected Area conservation context is pretty stunning. So prior to the inception of PIPA, there was just the Great Barrier Reef, and then PIPA came online shortly after Papahanaumokuakea, and then of course there's been this catalytic conservation movement across the Pacific. And actually, one more reason why you should love this place is that it's your next door neighbor. This is part of the United States Pacific Remote Islands Marine National Monument, Helen and Baker Islands, and so it's your next door neighbor protected area in the middle of the Pacific Ocean, only a couple thousand miles away. No big deal. If you need a cup of sugar, you know who to call. All right, so here we are, back in my box, or our box, and now hopefully you're looking at this a little bit differently, right? You sort of see all the oceanographic features, how far, how remote they are, but also how special they are. And what they really break down to is 4 ecosystems. You have the terrestrial habitat, the pelagic open ocean, coral reefs, and the deep sea. And as the co-chief scientist of this protected area, it's part of my job to do my own science, but also to facilitate and oversee the science program with the country and on behalf of the country at times, to bring all of these together to make sure that we don't waste this special opportunity and that we really make sure that we understand what's happening within and across these systems. So let's start with the shallow reefs. And let's start with a bit of a sad story. Everywhere you go on this planet right now, you will see the same story. You'll see percent live coral cover, and you'll look over time, and what you'll see is a decline in coral cover. Coral reefs are in trouble. This is not a secret. And it's pretty scary. And we're living at a time, right, in the past couple years, we've lost 2/3 of the Great Barrier Reef. We see trouble in the Caribbean. It doesn't matter where you go. The story is similar in that you're either seeing mortality, struggles for life, or symptoms of trouble coming soon. But the issue is, for me at least, is that this is depressing, and I didn't get into coral science to watch them die. I got into coral science because I wanted to know what made them live. And there are places on this planet which are still unbelievably, incredibly, beautifully alive. This is Big Mama. She is the largest shallow coral on our planet that we are aware of. She is in American Samoa, not in the Phoenix Islands. And she is 40 meters in circumference and is about 500 years old. And for context, that's about, it predates Columbus finding the New World. So she's been around for a long time, and she has survived everything we've thrown at her for the past 500 years. So how does she do it? What's her secret? And are there other places which are still fabulously alive, or places that can recover? And so really, are there places that are resilient? And when we think about resilient, it really breaks down into two pieces. You can either be resilient because you resist trouble, or you can be resilient because you can recover from trouble. And so I'm going to tell you a story now about Canton Lagoon, a special site called Coral Castles. And actually, Greg, this is for you. I believe this is you, or it's Rob. I'm not sure which. I think it's you. That is you.
20 pounds lighter.
I make no judgment here. That is Greg Stone in his element, underwater in Coral Castles. And when Greg first got there in 2000 and looked at this, he saw a pretty intact and stable ecosystem, right? Really large, beautiful table corals, delicately layered on top of each other, basically no free space. It was almost 100% coral cover and really large colonies, bigger than my wingspan. And that is a pretty special thing. It indicates health, it indicates growth, and it indicates stability, because they had clearly been that way for some time, because these corals can break really easily if they're disturbed. Unfortunately, the Phoenix Islands underwent a very, very strong thermal event. They got really hot in 2002 and 2003. At the time, it was the largest bleaching event recorded with 23-degree heating weeks. And it went from 100% coral cover to 100% mortality. There was really nothing left. And I want you to note a couple things. Yes, the corals are dead, but they're also flipped over. And there's also covered in algae, and the water isn't as clear because now you don't have all of those mouths cleaning the water, and you get all of these extra sugars put into the water column, right? Everything's getting tougher. It's different. It's hard to recover from this because you're putting yourself in a negative spiral. But I want you to notice something else. There's still fish, and they're still doing what fish do, especially what herbivorous fish do. They're eating. And they're eating algae, and they're keeping the space clean, and they're creating an opportunity for regrowth. And this is what happened. So you went from 100% coral cover down to almost a complete crash to pretty significant, but still fairly small regrowth in 2009, and then a doubling, and then a doubling. And the Phoenix Islands now look like this still today. We just had an expedition out there a month ago, and these corals look just as layered, only bigger. And so you can have recovery, even really fast recovery. And you can do this in places, even in the one island that is inhabited. So there are some special things about the Phoenix Islands and what we can learn about the pace of recovery. I'm going to tell you stories about the shallow reefs and the deep ones, but first, one of my favorite things to do is to show you, not just in pictures, but in video, what this place looks like. So I'm going to take you there. And my other favorite thing to do is to take scientists from one discipline, put them into another, and watch their reactions. So you're going to see a deep sea biologist, a dear friend of mine, Tim Shank, respond to the corals of the Phoenix Islands. If I could get a little help playing this movie, please. Thanks. We are standing on Canton Island, which is the largest atoll in the Phoenix Islands protected area, the only place where there is a resident population of Kiribati people who are caretakers of this really special protected area, which is the largest and deepest World Heritage Site on the planet.
Welcome, welcome to Canton, our beautiful island, peaceful and breezy. Welcome to our princess land. Welcome. Thank you, Harry.
have repaired a tide gauge, enjoyed the beautiful lagoon and the warmth of the Kiribati people, and we've only been here a few hours. We were snorkeling coral castles, which is one of the most spectacular sites on the planet, and it's a place that I was worried would have been bleached from the 2015-16 bleaching event, but it is a relief, frankly, to be able to report that I saw no signs of bleaching. And the reef, which had completely been destroyed in 2002 and 2003 and had so quickly rebounded, continues to rebound.
And we snorkeled on those things today, and they were teeming with life. They have come back with great force and great resilience. It was fantastic to see all the fish that were there, the blue ones, the pink ones, the green ones. For deep sea biologists to see shallow water communities of corals like that, it was fantastic. I've never
Oops, sorry.
seen anything.
Oh, nope, we stopped there. He's never seen anything like it before, but he's a deep sea biologist. But we'll get to the deep sea in just a few minutes, so these are all online, you can catch them there. So we were worried. We were worried that this place would have bleached again. The Phoenix Islands did bleach in 2002, 2010, and 2015, but they've recovered. And so now the question becomes, and this is where the science really comes into play, how do you measure this in more detail? How do you know what a healthy recovering reef looks like? How do you know when a reef in the middle of nowhere is headed towards regrowth and recovery or is headed towards demise? And that's really challenging because even though we run expeditions out there every year, every expedition is different. When we're running deep sea expeditions, you need one kind of ship with one kind of set of technology and tools. Open ocean expeditions, totally different situation. Coral reef expeditions, one every 3 or 4 years, and you get an hour at each site because an hour is all you can handle when you've got a metal tank strapped to your back. And you go in, you jump in the water, you get 1 hour in a site, and you move to the next one, and in a couple of weeks you're done, and that's all you get for the next 3 or 4 years. So you have to build some tools. So in collaboration with Scripps Institution of Oceanography as part of their 100 Islands Challenge project, we have 8 of the 100 islands, so 8%, pretty psyched about that. And what we do is we go down and we send a camera system down with a diver, and they very, very carefully will take like 10,000 images of the seafloor. And we stitch them all together using photomosaic technology and orthoproject them with incredible precision so that you should be able to see growth or death of corals within a few millimeters of each other when they're all perfectly overlaid. And with this, we have 2 things. One is we have an archive of corals. We have an archive of history. We have a time capsule that we can go back to again and again and again, as many times as we need to ask questions later that we might not have thought of at the time. The second thing that we can do is over time, when you have this spatial view of the seafloor, you can start to ask really important spatial questions like, how do things regrow? Are they always the same species that come in first? Does one species help facilitate another species coming in to grow? Does one species prohibit another species from growing? What's the tolerance of these? How do they look? How does this work? And this is an incredible amount of work, but it's worth the time because you do this once under the ocean. And then we have teams of students who trace every single individual coral by species. This is absolutely painstaking work, and my students deserve a ton of credit. And they do this with great precision because they love the idea of being able to watch corals grow carefully. And if they trace a few millimeters off, right, then all our data are off. So we do this with incredibly high precision with much more close-up views of every single coral as we go. But they do this, and eventually over time, you can get a map of where everything is and color code it by species. And if you take a look here, this is sort of the zoomed out view, but you can see that this species, this individual, is the same as this individual, spaced 3 years apart. And we can really start to look at change. And what I will tell you so far is that we've been surprised in both directions. Some corals have held on when other corals have died. Some sites have boomed in 3 years and have just grown faster than we ever could have expected. Whereas other sites have died, and we don't really know why, because it happened over the same 3-year period. So what we do know is that we have a lot to learn from this, and that we're committed to this technology, or this kind of technology, for at least another decade. And hopefully, as we amass this data set, we'll be able to really answer detailed questions about spatial ecology in this system. The other reason this is important is that these are all pictures taken from the Phoenix Islands at the same point in time, although slightly different points in space. And so recovery and resilience and ecosystem succession is not going to look the same at each site. And when you have a place that there are no people, there's no coastal runoff, there's no disease, there's no overfishing, there's the majority of plagues that really harm coral reefs everywhere else don't happen here. We have a chance to look at nature just in nature, and that's an ever rarer chance these days. Okay, next vignette. Let me tell you a little bit about the ocean around these coral reefs, because when you really think about it, these 8 tiny specks of islands, right, have just 8 tiny little specks of reef, and the vast majority of the Phoenix Islands is open ocean. Open ocean oceanography is pretty exciting, and it's a little challenging. So, you have to go out with a pretty specialized set of tools. And you can take even the simplest thing like temperature, which is something everyone knows how to measure. But when you're talking about the whole water column, it looks different. So the way to read these graphs is here's 0, this is the surface, and this is depth going down to 600 meters. And this is time, 2014, 15, 16. We've taken these data in 2017 and 18 too, right? This is a long-term data set. And here's the cruise track, which is the same every year, right? 1, 2, 3. And then you take a look at temperature, and here's the south boundary of the Phoenix Islands, and here's the north boundary of Phoenix Islands. And you can look at a little bit of a temperature wobble, right? As you go from year to year to year in depth, for example, right? You can see that this is much higher. It's about 200 meters, whereas here it's a little deeper, 250, 300, right? So you can see the changes. And this is in collaboration with the Sea Education Association, specifically with Jan Whitting. And he's gone out and he's measured temperature and nitrates and phosphates and chlorophyll A and phytoplankton and zooplankton. And every metric that you measure, you get different stories, which really shows you how different the ocean can be. Here's 2014 nitrates, and if you take a look at the ocean signature, it's fundamentally different through time, right? So you can just see the changes. And this indicates that we have a lot to learn about this ocean. It's not static, it's highly dynamic. Here you go again, this is fluorescence, chlorophyll A fluorescence, which is an indicator of phytoplankton, and you can really see the influence of the islands through space. You can take a look at zooplankton concentration marked by the circles. The larger the circle, the more zooplankton they are, and you can see that they're circles of all different sizes, indicating, again, a highly dynamic ocean. So what we do is we tow nets through the top, 50 meters of the water column, in sort of like a tow-yo fashion, right? Tucker trawls and Newstone tows, and what we're doing is we're looking for everything. This is the water cooler of the ocean. This is where the deep sea critters, the open ocean critters, the coral reef critters all hang out as plankton, as little baby larvae at the surface. And if you comb through what those nets bring up, you'll find a treasure trove of all of the critters that will have the chance, at least, of becoming adults in this special place, as well as all of the critters that feed them. And so this is what this looks like. And you get all of these bottles in the bottom, and these get sorted and put into a single jar. And in that jar is magic, right? Or science, depending on how you want to view it. But this is what fuels our ocean, right? Here's our phytoplankton. Here's your zooplankton, full of all kinds of really important critters. I mean, this is the food chain, right? This is what fuels everything. And the really important thing from this is that we have to answer some questions about the Phoenix Islands, and we have to do it with plankton. And let me explain why. And then so just hold on to this thought, and I'll come back. So here's the box. Here's the Phoenix Islands protected area. And I told you it's a fully no-take protected area. And so what I want, but that wasn't always true. It was a phased closure. So each one of these lights represents a fishing vessel that was present in the area. And this analysis was done with Global Fishing Watch and Google SkyTruth. And what you can see is the halo around each of the 8 islands, which represented the initial phase of closure for the protected area, or 12 nautical miles. And then January 1st, 2015, the protected area fully closed, and it went from being fished around, outside of the halos to being unfished. And now here comes the really important question, the one that everybody wants to know, which is when you fully close a marine protected area so that it's no take, does it work? Do you see an increase in fish stocks? Do you see an increase in vibrancy? Do you see an increase in ocean health? And the truth of it is it's hard, most of the fisheries data that we get come from fisheries. They come from people fishing. And so everybody wants to know the answer to this question, and they want to know specifically about tuna. Right, tuna is big business in the Pacific, and everybody wants to know whether or not we're seeing an increase in tuna, an increase in skipjack, yellowfin, bigeye. And I'm the co-chief scientist of this protected area, and so when people come to me, I look at this and I say, my God, I can't answer this question with this fish. This is too hard. But I can answer the question with this fish, which is, only if I can make it work, which is the larval version. Right, so we can use these plankton tows to answer questions about all the critters, right, including coral reef fishes and lots of stuff about the deep sea, but importantly about something like tuna. Now, it's been an assumption for a long time that we would find larval tuna in the Phoenix Islands protected area because it's been an assumption for a long time that they were spawning in the protected area. And in order to really answer this definitively and not just assume it, I have tons of students, again, who deserve a ton of credit, who sort these jars. We get about 100, we go to 100 stations a year approximately, come out with several hundred jars, and it takes a really well-trained, super taxonomically savvy undergraduate in my lab 10 hours to look through a jar. And they pull out all the ichthyoplankton, and in collaboration with Joel Lopez and Christina Hernandez and Jan Whitting and Simon Thorold, crossing SEA and the Woods Hole Oceanographic Institution, we pull out all the larval tuna, and this is what a bunch of baby larval preserved tuna look like. Pretty cool. We then have all kinds of questions, like, all right, well, we found larval tuna in the protected area, but were they really spawning there? How do we know? And so it turns out that these itsy-bitsy little fish have even itzier, bitsier little ear bones that we can pull out and dissect. And when they're little, each one of those ear bones lays down a ring for every day the fish was alive. So you can open up a fish's ear bones and figure out whether it had been alive for 3 days or 12 days or whatever. And if you measure where it was taken, and you know something about the currents and the oceanography, which we do, then you can figure out that if this is 3 days old and the currents were doing this 3 days ago, then it was probably spawned here. And we can run larval backtracking models. This was done by Christina Hernandez from Hui. She's really great. And we can show you that these fish spawn in PIPA. Skipjack, yellowfin, big eye. And we know over time, right, we're on year 6 of this study, and we're in for at least 10 years. We'll be able to answer whether or not they always spawn here, or whether they follow the water parcel that moves here and here and here and here over time. And so we know that they spawn, but now the question is there high fidelity in their spawning sites? How important is this place versus another place in the ocean? And a whole lot of other questions that we can answer too. We use genetics to barcode these to make sure that we know what we're looking at. And this is a bunch of tuna eggs. I mean, they're just super cool. I mean, when was the last time you've gotten a chance to see a tuna egg, really? Ever? I don't know. Here it is on the big screen, just for you. And we can start asking questions about nutritional composition, lipid composition, health of the tuna. Eggs might tell you something about the health of the reproductive adults. And so there's a whole wealth of information in these samples and in these jars that is going to unlock some secrets for us in this really hard to get to part of the ocean. We're not just going to do this for tuna. While we're sorting through these jars, we're looking at all of the fish, coral reefs, deep sea, open ocean. We're also looking at a lot of the inverts, including coral larvae when we can find them, some of the crustaceans and other things. And so over time, we will amass a large data set that will tell us, we hope, a lot more than we ever thought we could possibly know about the dynamics of this really exciting and really basically as untouched as it gets, protected, it's a really special place in the ocean. Let me move to the deep sea, because this is really important. If you had asked me a year ago or a year and a half ago what I knew about the deep sea in the Phoenix Islands protected area, I would have just shrugged my shoulders and said, I'm sorry, I don't know anything. It's a priority for us, but we haven't been able to get out there. And then last year, something amazing happened. In collaboration with NOAA and their Office of Ocean Exploration and Research, OER, and in collaboration with the Schmidt Ocean Institute, which I know Jerry works with both closely, we were able to use, in part, taxpayer dollars, so thanks to all of you, to get some resources to go out and look at the deep sea of the Phoenix Islands for the very first time. And this was really special. In really 1 year, we were able to do 25 dives and bring the mapping total up to 21% mapped. Maybe. Let's see. Okay, so here's what the map looks like of all of the areas that are mapped, and everything that's in rainbow has had a pretty high definition, a multi-beam map sort of made of it. And I know that you're looking at this going, so what, there's a bunch of rainbow lines in a map. But this is really special, and here's why. So this was done on purpose. This was done by Brian Taylor at the University of Hawaii. He's looking for evidence of seafloor spreading or joining, trying to understand the seafloor dynamics. If you're a geologist, you get really excited about this stuff, and you can do it with just a map, which is pretty cool. If you're me and you're looking around this, you're looking to say, oh gosh, is this seamount really a seamount? Because before, all I had were these blue blobs on a piece of paper, and somebody's going to ask me what resources are in the Phoenix Islands, and I'm going to have to say, I don't know, count the blue blobs. Who knows if they're real? So I'm really happy to have a real map, right, that shows me something about what's really happening in this area. So, and this map is also really important because when you take a deep sea expedition out and you're taking an SUV-sized robot and you're going to drive it on a mountain to try to look at corals, you need a detailed map. And this, which is what we had before, just ain't going to cut it. So we had to make maps that look like this. And when you bring the two together, you'll see how wrong we were before and the power of a really beautiful map. And this is thanks to NOAA and their team of incredible mappers at UNH and OER who were able to help make this. I can't go on every expedition, and I always put this slide in because I think it's important for you guys to know that I'm also a mom of 2 little kids, and they can sometimes do this in my lap. This is my home office, and we can do deep sea exploration via telepresence. The whole world gets to join in sometimes, and you guys can do this too. Whenever there's deep sea expeditions going on, you guys can do this. I've been to the Phoenix Islands a number of times, but I also run a lot of these and participate in a lot of them on telepresence with my kids, and I think that inspiring the next generation of ocean stewards happens even at home. Okay, so how do we do this? How do we do deep sea exploration, and what do we learn? So we spend all this time making a map, right? And sometimes with kids in your lap, but you do it. And you make this incredibly detailed map of the mountain, and you really think about it, and you say, should we go look over here? Should we go look over here? Where should we go? And you decide by consensus, usually if you're with OER, or with your whole team if you're on a different ship. And everybody sits there and thinks about it, and we say, yes, we figured out where we're going to go. Here's where we think we can go. In about 10 hours, we're going to do this little trek right here. That's all we can afford to do. That's all the time we have. So, all right. I bet most of you have climbed a mountain at some point in your life, yes? Or taken a car up to the top of a mountain. The best part's the top, right? When you've worked so hard and you get this vista with all of these views. In the deep sea, what you get is what you can see with your flashlight, because you're doing the whole thing at night. There's no light down there. So you climb this mountain, and all you can see is what you see in front of you, what you can light up. But it's really worth it, because even with just these tools, and even with this small area, I show this to you so that you know that when people say, they've explored the Phoenix Islands, no, we haven't. We've mapped a mountain, and we've done one itsy-bitsy little trail on the side of one tiny seamount, right? We have so much more to do. But even with the little bit that we've done, we've learned a lot. Could you play the movie, please? Thanks, Robert. We work with engineers, we work with biologists.
Biology
we work
is
with
always
pilots.
a big inspiration for engineers. There are many things we can learn from nature. Looking at an octopus, the way it moves its body, the way it would grasp an object, it's very interesting to see.
We followed it for a while, sort of forgot what we were doing for a minute. Those behavioral observations are very valuable in this, just documenting this really rare species in the middle of this giant protected area. It continues to build evidence for the value of this really precious resource.
As you become more familiar with an area, you can kind of decide, like, okay, yeah, we definitely haven't seen that in these 6 dives that we've done in this general area, so we should collect that.
Okay, can you pause for a second? Can you pause the movie, Robert? Oh, okay, good. I just want to set the scene for you guys so that you guys know what's going on. So we take these ships out. It's an incredible, there's 3 years of planning. It's a whole lot of work. And then you don't know what you're going to see, right? You go down, you're there. Like, everything is a first. First time we've dove on this seamount. First time we've been to this space. First time anybody's seen this species, right? We discover new species all the time. And then something like this happens. So what we are on is we've approached a vertical cliff. You can kind of see it. This is the robot's point of view. This is the top down looking at what's happening. And we're in this vertical space, and we're going to ask an ROV pilot to go and pick up a sample. Now, there's always a scientist driving the science camera and kind of running the dive, and then there's the ROV pilots who are actually operating the machinery, and the whole thing feels like you're in the command center, working with NASA, because you've got like 38 screens and 6 people, and it's dark, and it's super intense in there. And this particular ship, you work around the clock, which is really an exciting opportunity. I love that, but it's, God knows what time of the morning, and you have 100% of your energy focused on, in this case, picking up a brand new crab that might be in a whole new genus. And I'm going to, at my own risk of my own embarrassment, I'm driving the science camera. We've got some great ROV pilots on the controls, and I have the whole science team behind me, you know, not making me nervous or anything, just looking over my shoulder saying, yeah, get the crab. And so I'll show you what this is like. Could you play it again, or right from here?
Yeah, we're even gonna try this. It's just in a very precarious place. It's been reported as being a new genus, so this could be something really new. They're on it. Right there, right there, right there. They're on them. Did you get it?
They're using a vacuum suction sampler to try to pick it up. And it's super stressful because you can drop it at any time.
Put them down in the box. Cut suction.
It is not
And
over
close the
till it's
lid
over,
quickly.
people. These crabs can climb, they can swim
He's in
out.
there.
Don't
It's
celebrate
in
yet.
there.
Nope, you can't do
It's
it.
got eggs.
Now you can celebrate. It's in the box. And sure enough, it's definitely a new genus, and we're pretty excited. But these are the kinds of discoveries you never know what you're going to make.
Samples are absolutely critical for what we're trying to do. The questions we're trying to answer here about the evolution of life in the deep sea, the evolution of life in this area, plays into the larger role of how communities shift and change with climate and with protection.
You start a trip with an empty box and a lot of hope, and really no idea what you're going to find. And then dive by dive, the box starts to fill up. The ROV pilots, the scientists, everybody is working together to be able to identify samples, to collect them and bring them up safely so that we can study them and learn something about them.
Sometimes when I speak with biologists, they tell me that they see something they're interested in, but they don't even try picking it up. They know that it's not going to work. The manipulator is going to crush it.
You know what? This is too much. No.
No.
We're going to leave it.
Daniel Bode got a chance to try his squishy fingers in situ, right in the deep sea. Soft robotics technology that was developed on the ship.
Yeah, nicely done.
He would
Soft
3D
robotics
print
is
them
a
on
field
ship, and
where
then
we
we'd try
try
to
to
bring them down.
expand the materials that we are using, and they are extremely soft. You can compare that to a rubber band or even to gummy bears. And this allows to grasp things that we wouldn't be able to grasp with a hard-bodied manipulator.
So he would try them, we would redesign them, he would print them instead, and then eventually we were able to sample something like a sea cucumber, which you could never
Now
pick
that
up
I've
with
seen
those
them
hard
in
robot arms
action,
from before.
there are more and more things that come up that we're trying to collect that seem to fit that very well.
These other samples are critically important, and they're put into liquid nitrogen and ethanol, and they're stored in RNA later, and they're going to have transcriptomics and genetics and population genetics, and maybe in some cases even genomics performed on them.
A lot of medical researchers who study marine bacteria are actually looking for different structures that can interact with our immune systems in different ways that could be beneficial. A lot of what my project is based on is wound healing.
We've seen sea stars that are eating the corals that are predatory.
I can actually isolate the wounded tissue and separate it from intact tissue to hopefully be able to determine what kind of patterns and recognition of microbes these animals use to regenerate over time.
Modern day discovery may not be as romantic as people might have in their heads, but what it is efficient, fast, and amazing. The idea that you can go from knowing literally nothing to then making a map, taking a bunch of water samples, putting a bunch of sensors in the water, getting visuals down there, getting animals in your hands, preserving them so that we can look at them in every possible way with every possible tool available is just incredible, priceless, and that's what these samples are. If you asked me to put a price on them, I couldn't. So, a year and a half later, we know all of this, and we still know nothing. We still have so much further to go. Could you advance to the next slide, please, Robert? Thank you. And how do we use all of this, right? All of this deep sea work and shallow ocean work and everything. We put it together, right? Before I showed you this map, and you may not have noticed this boundary dispute, but this was everyone was trying to decide. It's a little complicated, but this little group of seamounts is Winslow Reef, and the decision had to be made by the Republic of Kiribati whether or not to have the green boundary or the teal boundary. And among many other things that helped the decision is we were able to take the information that we had, give a much better map, show what was there biologically, show that it was important, and helped make the case that Winslow Reef is worth protection. And sure enough, the teal line is the actual boundary, not the green one. We use this in the conservation context of the Pacific to set baselines and to try to understand what's here and what might be next door. we find all kinds of species that we didn't know were here, and some of which have been known for a while, and they have various important properties. And we find places, we get to explore places that we've never seen before, like this Hadal Trough right in the middle, this really, really deep hole. And even down here, right, there's life. There's a monoplacophoran, which is an ancient critter, really, and this is a half-meter long sea cucumber that manages to find enough food to grow that big, way down below 6,000 meters in the bottom of the sea. And by the way, the sediment that it's eating is carbon sequestration from the ocean atmosphere that's come all the way down there, and this is what they're working on. We find corals, which are as tall as the ROV, that are ancient species that have been alive for not 500 years like Big Mama, but 1,000 years. I mean, the oldest coral in the deep sea that's been found alive is about 4,000 years old. The most ancient deep sea creature that's been found is a sponge off of the South China Sea that's 18,000 years old. And these critters have made it through all of human history in this land of giants, right? And they are living in the Phoenix Islands protected area. They're living all over the ocean, and we are just now getting the technology to know that they exist. People always ask how I know how old they are. These two dots are around 10 centimeters apart, and if you know something about the growth rate of a related species, you can sort of measure the base and get a sense of how old things are. This is a really cool Jasonisis, or I don't know, a bamboo coral. So you find new species all the time. Ooh, I don't know how this is clicking, I'm sorry, but this is probably a new species of coral. There's a brittle star on it. Like I said before, there's all of this sediment, and don't think it's just sand. This is important. This is how the ocean stores carbon. There's a whole bunch of critters that live here too that are unique to this system. It doesn't matter where you look. There's something new to explore and something new to learn. Science is about hypothesis testing, but it's also about exploration. And one hand is the right hand is exploration and the left is hypothesis testing, and you bring the two together and you figure out how the world works. And I'm lucky enough to have a playground like the Phoenix Islands to work with and in with so many collaborators. We have about 75 scientists now who have had the honor and privilege of working in this special place along with the Kiribati people to look at this crazy, incredible, beautiful, stunning conservation context place, this spatially explicit integrative ecology project where we don't just have to look at the surface anymore. We know that there is so much more below it. And so with that, I hope that you look at this box with a little bit, with new eyes. The simple goal here is, for me as a co-chief scientist, is what's in the box, how does it work? But like I said before, I'm an outside-the-box thinker, and what I really want to know is how does the Phoenix Islands, and what can the Phoenix Islands tell us about the rest of the Central Pacific, or the rest of the Pacific, or the rest of the world? And how do all of these things link together? And so for the places on our planet where nature still is natural, we have an opportunity. And those opportunities are rarer and rarer these days, and it's the honor of my life to work on this project. I don't do it alone. I do it with a lot of help and support with many, many collaborators and many institutions who support us. And to all of them, I say thank you. We couldn't do this without you. But most importantly, when people talk about the blue planet, sometimes there are special places, even in the part of the globe that nobody turns to. Thanks, guys. And I'd be happy to answer questions. Thank you.
Thank you, Randy. And Greg, thank you for inviting this aquarium to join the board of directors of PIPA. We have a meeting coming up in New York City, end of next week, is it? That's right. Yep. So we'll be there. All right, questions or comments?
Jerry, thank you for providing the leadership when this work started some 18 years ago when I was working for you. This wouldn't happen without you.
That's true.
Thank you. Who has the first question or comment? We'll start here. Come back to you.
The pictures of the coral degradation and bleaching were impressive, but what was more impressive was the quick rebound. What changed? What caused it? What changed to allow it to bounce back like that?
So that's an excellent question, and actually you have a speaker coming in just a few weeks, and Dr. Ann Cohen, who's going to talk a lot more about that in great detail. But in this particular space, the cause was almost certainly the high temperatures. Right? It had 23-degree heating weeks, which was the largest and most acute high thermal event that had happened in that particular site. And it was brutal, and so there were 7 months of sustained high temperatures. As for the regrowth, I think there's a couple of factors. So first is that there were all of those fish keeping the reef clean, which provides an opportunity, a spatial opportunity for corals to rebound. Second is that there was enough larval seed for those corals to come back, which is really important. If you don't have a source of new baby corals, you can't get new corals. And third, this is what happens when you don't have overfishing, and you don't have coastal runoff, and you don't have disease, and all of the other things that plague reefs that are closer to shore. And so it's not always quite that simple. There are certainly spots in the Phoenix Islands that have not rebounded as well, and we think that there's a complicated story of it's a little bit of thermal history and a little bit of nutrient acquisition and a little bit of species-specific context. So, I mean, the unsatisfying but true answer is that it's always a little complicated, and more so than we ever thought. But in this case, it's a pretty straightforward case of a very fast-growing coral that had all of the right tools to regrow quickly, and didn't get interrupted.
We have one here.
So how did you guys even get started with this entire thing? Like, how did that even happen? It seems like something that is so immensely amazing that, how did it start?
So you have the experts in the room. You have both Jerry and Greg here, so I feel like I'm not going to tell their story for them. I'll answer it from the science perspective, and then if you guys want to tell your story, this would be your moment.
We'll let Greg do it, but you go ahead.
The science piece of it was just that Greg handed me the reins at the right time, and I took a look and said, what can we do with this space? And brought in a bunch of people and really listened and really thought carefully and deeply about what we wanted to do, charted a course, did it, but we weren't super strict with our plan. We let exploration take us and guide us in new ways, and we're still building this. I mean, you could say, she's been at this for 10 years, don't we know everything already? No, we have barely begun. So for me, it started with the science, and I have a whole lifetime ahead of more than I could possibly do, right? But a huge team behind me to help pull this off. But the story of the Phoenix Islands belongs to these two.
Well, no, I'll mention briefly. I had the great pleasure of working for Jerry Schubel at another place, and I don't know. I think he was always trying to get rid of me, because every time I had some crazy idea to go off diving, either into an iceberg in Antarctica or to some remote atoll region of the Pacific, he'd let me go. But I always managed to come back. But no, seriously, this started kind of by chance. I was asked to go on an expedition based out of Fiji. Somebody wanted to explore this group of islands that had never been dived, and I'd never heard of the islands, in a country that I'd never heard of. And I said, maybe, and then when I found out they had never been dived before, I said, I'm in. So I was basically interested in kind of the exploration. And then I got there, and it was under the sponsorship of the National Geographic Society. I've written 2 stories for the magazine on the Phoenix Islands. If you want to Google those up after tonight, you can read them. And when I got back and I realized these reefs really represented what I'd never seen reefs like this. Suddenly I understood the ocean in a whole new way. These are what reefs were supposed to be like. They were not there. And I made my way to the people that owned the islands, and we have a person from the country here tonight, and basically presented the findings, and then the country stepped forward and created this massive protected area at a time when no one was doing this. They were very prescient in their actions and really led the world in the area of marine protection.
Thanks, Greg. All right, who has the next question or comment? We've got the microphone back there.
Hi. How close do fishing boats come to that area? Because it seems so remote.
So prior to full closure, they were fished all the time. The Central Pacific tuna fleet is large, vast, and powerful, and that's where the tuna are, so that's where the fishermen are. Post-closure, people really respected the boundaries. Everyone has a right of free passage, so ships still occasionally transit through, but for the most part, they don't. And yeah, so now people you'll see them on the boundaries all the time, but if you use satellite to look, but no, they really, for the most part, stay out.
We have one right here.
Hi. So what do you find to be the priority in the next phase of the research?
You want to know our secret plans. I'll tell you, but this is only broadcast live, no problem, right? So we're still forming them. And I think the real trick of running a successful science program is to listen really carefully to the country that owns this, as well as to the scientists who have worked there. But for us, the priorities are probably going to come down well, many things, but there's a couple of really clear things which are obvious to me. First is continued exploration. We still don't know as much as we need to, but we're much better off than where we were. And that includes exploration of the mesophotic, which we really haven't paid any attention to yet. We've just a tiny little bit, which I didn't even go into today, but that's a real priority. The second is going to be to really do a much stronger job of connectivity, really doing the population genetics to understand where the source and sinks are for the Phoenix Islands. So if something dies, like I told you, you need new baby larvae to reseed it. So where is the source population for the Phoenix Islands? Where is one source going to come from? Where are they going next? And then where do the Phoenix Islands larvae go to? Did they just get swept out to sea, or did they help reseed another spot? What is the connectivity across the Pacific? But for me, and this is something that wasn't in the original plan, but it is what I presented to you tonight, all of the really big novel pieces are going to come from the intersections across these ecosystems and really looking for the interconnectivity. And that's something that you can really only do if you work across all of these systems and in a single space. And so it's a huge space, and I can't do it alone, but I'm really excited to sort of look at the interplay between systems. And so we'll see what else we come up with. You can read our 10-year plan in 2 years when we write it. I can shake my crystal ball or magic 8 ball or whatever, but I won't come up with a clear answer for you right now.
So when you're thinking about huge spaces, if you look at that image on the screen, I used to study the Atlantic. You could put the Atlantic and the Indian Ocean into the Pacific and have space left over. Sometime, if you're interested, there's a very humorous clip called Radio Show with Woody Allen. They're arguing about what ocean is the largest.
Yes. Oh, sorry.
When you are exploring and taking samples of creatures that perhaps have never been seen before, what consideration do you have for sustainability or preserving that creature? Is there a fear that this might be the only one that you find?
Generally, thank you for asking for that question, because let me just first say that I take our responsibility as scientists extremely seriously. We don't take something we don't intend to use. We don't take something without thought or care, and we go through a lot. We ask ourselves these questions all the time. When we're taking a piece of a coral, we're lucky. It's pretty easy because a coral is a colonial animal, and we can take a piece of it and it'll generally regrow. We don't kill the genotype almost ever. So it's like taking a little cut, a little biopsy, and letting it regrow. When we take a crab or a fish or something where it's the whole organism, we've actually passed up quite a lot of things where we've said, it's the only one I've seen, let's not take this one. And then we'll wait and look around a little bit, maybe spend a little extra time exploring in that region, and usually you'll find 2, 3, 4, and you'll realize, this is their habitat, okay, I'll take one. It has to be something that we're pretty sure is really special, because you're never going to be able to go back and find it again. For us to take the whole thing and not see a second one, I haven't done that yet in my career. I'm sure other people have, but nobody's done it lightly. It's something that everybody really thinks about. And there can't just be one in the ocean. But remember, we have these huge mountains. We're taking a tiny little trail. You take one little organism, and you do this once. We've only been to the deep sea twice total in the history of this place. So the chances of us fully exploiting this are slim to none. But we do, even then, take it extremely seriously. And it is a decision that we make in order to advance science, and we try very hard not to harm the system. But thank you for bringing it up. I think it's really important that everyone knows that scientists are human, and we really think about this stuff before we do it. Thank you.
Other questions or comments? No? Well, then join me, please, in thanking Randi for a wonderful talk.
Thank you very much. Thank you for the invitation, really.
And our next program is on October 4th. We're going to have a panel discussion about marine aquaculture. We hope you'll join us then.